This function is all about substituting into your integral a new trigonometric function to replace the original variable, and then using the nice geometry and the nice properties that trig functions have to allow for some simplification. So you have a constant plus x squared. I need you to think of tangent. If you have a constant minus x squared, I need you to think of sines. And if you have x squared minus constants, I need you to think of secants. These turn out to be the correct substitutions to see that nice cancellation and to use those properties. So example 5.1, we see a constant plus x squared. That, to me, reads that we should use the tangent substitution. We want to give a family of antiderivatives for this function, 1 over the square root of 4 plus x squared. So we want to integrate this. Now, that 4 plus x squared, to me, says tangent. So I'm going to replace x with a 2 tangent of a new variable, call it theta. And the reason I chose that 2 is because we are recognizing 4 plus x squared as 2 squared plus x squared, right? That's a squared plus x squared. So the a here is a 2. Now, with that choice, we can find our differential dx as 2 times the secant squared of theta d theta. And now our integral becomes the integral of 1 over the square root of 4 plus x squared. I want to go ahead and keep doing scratch work to go ahead and replace that all in once. So the square root of 4 plus x squared will be the square root of 4 plus x squared. But I'm replacing the x's with 2 tangents of thetas. So distributing this square to the 2 and the tangent separately, we have 4 plus 4 tangent squared of theta. And I can pull a 4 away, leaving us with 4 times 1 plus tangent squared of theta inside that square root. And if you're good with your trig identities, you can recognize that 1 plus tangent squared as a secant squared. That's why tangent was the correct choice. This 1 plus tangent squared is now a secant squared. Oops. And that square root can distribute across the multiplication. The square root of 4 is a 2, and the secant squared and then being square rooted returns a secant. All right, so I can replace that square root as a 2 secant of theta. So square root 4 plus x squared replaced with a 2 secant of theta. Now we have to replace this dx. The dx is replaced with a 2 secant squared theta. d theta. All right, and now we see a lot of cancellation. We have the integral of the 2's are gone, and then I have secant squared divided by secant. That leaves me with 1 extra secant on top. And the integral of secant is known to be the natural log of the absolute value of secant plus tangent. And we have our arbitrary constant of integration plus c. So we've used the nice geometric properties between trig functions to integrate this. We no longer have the integral sign, but it should be our next step to go back to x's. Right? We created this new variable theta. We should go back to x's. But secants of thetas can be replaced with 1/2 of these square roots. So we have natural log of secant theta is 1/2 square root 4 plus x squared. And tangent of thetas is replaced with 1/2 of x's. So now that's a good antiderivative for 1 over the square root of 4 plus x squared.